a hemisphere, okay? So this is the hemisphere, that's the top, and this is the bottom, and let's say here we're going to have two axes. This is going to be the north, and this is going to be the east, okay? And in this stereonet, this is a half hemisphere projection. It's not a stereonet itself, okay? But we'll get there in a bit. In this, with this tool, what we're going to do is I'm going to map this fracture over here. So that plane in this geometrical object is going to be a plane that we know the strike very well. It's going to be that, all right? So that strike is the same as that. And we know the dip too, and the dip, let me continue. So that's going to be that line. The dip is going to be a plane that is going to intersect the lower hemisphere somewhere. I hope this comes well. So this is the bottom. It's going to, it should have gone all the way through there, okay? So it's going to come through here. So this is the line of maximum slope. And this is the same plane as that plane over there. So you could say, well, actually, this is more complicated than what you did before. So how is this going to be easier? Well, a plane is defined by a line perpendicular to it. As long as you have one line perpendicular to a plane, you know what the direction of a plane is, because that line is going to be unique. And in this case, it's going to be the same. We're going to draw here a perpendicular line to this plane. And probably this is not the best orientation to do this, but I'm going to do this again one more time later on. And let's say that it's that line. The point at which that line touches the lower hemisphere projection, that's going to be the dot. So this 3D, if I have a top view, this is going to be the north, this is going to be the east, this is going to be the plane. It dips into this direction. No, oh, sorry, dips into this direction, and so a line perpendicular to it is going to touch the lower hemisphere projection in a point somewhere over here. And that's the point that we plot, that is going to give us what is the strike and what is the dip of the fault. So let me zoom with this on this, and so it's that plane, you see? So that plane over there, if I grab the same color, red, I have a line perpendicular to it. The point at which the tip of the pen touches that lower hemisphere is going to be that point. If I have, for example, a vertical plane, the tip of the pen will touch the lower hemisphere projection here. So how far the points from the center tells you the dip. This is going to be a vertical plane. This is going to be a horizontal plane. And where this dot locates corresponding into this direction is going to tell you the strike. For example, if you have a vertical plane, you see that a point over here will be strike east-west. A point over here will be strike north-south. And if you want to add a little bit more of detail here, we can break this circle into 3 circles, right? So we said that here we have a dip 90 degrees, and let's say this one is 60 degrees, this one is 30 degrees, and here you already have the strike. So remember that the strike will be perpendicular to this line, perpendicular to that point, not that point itself. So you find the point, you draw a perpendicular line, that's a strike. And if you do that, now we're going to be able to plot thousands of fractures in the same formation, and our objective is going to be to try to understand which of those fractures have the highest shear stress and corresponding to the in situ state of stress. Okay, so all right, guys, this is it for today. Have a great weekend. I'll see you on Tuesday, and don't forget that you have a lab, a triaxial lab next week. Okay, so show up on time and wear long pants. Okay, if you don't wear long pants, you won't be allowed to get in.